Hello friends, and welcome back to another journey through deep time. I'm so glad you found your way here tonight, to this quiet corner where science meets wonder, where the impossible becomes real through the gentle art of storytelling. Whether you're curled up in bed, sitting by a window watching the rain, or simply letting your mind drift towards sleep, you're exactly where you need to be. Tonight, we're traveling to a moment in Earth's history that sounds like something from a dream, or perhaps a nightmare. Imagine stepping outside and feeling the first drops of rain on your skin. Nothing unusual there, but then imagine that rain never stopping. Not for days, not for weeks, not even for years. Imagine rain that fell continuously for 2 million years straight, transforming our planet into something utterly alien, something that would reshape the very foundation of life itself. This isn't science fiction. This isn't mythology. This was real, and it happened during a time called the Carnian pluvial event, roughly 232 million years ago, when the skies opened and refused to close again. Before we begin this journey together, if you find comfort in these quiet explorations through time and space, I'd be grateful if you gave this video a gentle like and perhaps subscribed for more peaceful adventures through science. And if you'd be so kind, let me know in the comments where you're listening from tonight and what time it is there. There's something magical about knowing our little community spans the globe, each of us finding wonder in the same ancient stories. Now, take a deep breath. Let your shoulders soften and step with me into a world where the very concept of dry land had almost disappeared, where evolution was forced to rewrite its rules, and where the stage was being set for the rise of the dinosaurs. The world before the endless rains was nothing like the one we know today. Picture in your mind a vast supercontinent called Pangaea, stretching nearly from pole to pole like a colossal island surrounded by one immense ocean. This wasn't the diverse, temperate world we inhabit now. Instead, much of Pangaea was dominated by harsh, arid landscapes that stretched beyond the horizon. Deserts covered enormous expanses, broken only by scattered oases and the occasional river winding its way toward the sea. The climate was hot and dry, almost oppressively so. Rainfall was sparse and unpredictable, coming in brief, isolated bursts that did little to soften the hardened earth. Plants clung to life along coastlines and riverbanks, forming thin, green ribbons in an otherwise brown and dusty world. These weren't the lush forests we might imagine, but hardy, drought-resistant species that had learned to hoard every precious drop of moisture. Life had adapted to this harsh reality in remarkable ways. Reptiles dominated the landscape, their scaly skin perfectly designed to prevent water loss in the relentless heat. Early archosaurs, the ancestors of crocodiles and dinosaurs, prowled across the plains, while various other reptilian groups claimed their territories. These creatures had evolved efficient kidneys, specialized skin, and behaviors that allowed them to thrive in conditions that would challenge most modern animals. In the scattered wetlands and along the rare permanent rivers, amphibians maintained their ancient lifestyle, though they were increasingly pushed to the margins by their more drought-tolerant reptilian cousins. The air itself was different then, richer in oxygen than today's atmosphere, which allowed insects to grow to sizes that would seem monstrous by modern standards. Dragonflies with wingspans approaching those of small birds patrolled the skies, while massive millipedes and other arthropods scuttled through the undergrowth. But perhaps most importantly, this was a world of stability. For millions of years, the climate had remained relatively consistent. Ecosystems had found their rhythm, food webs had established their delicate balances, and species had settled into specialized niches that seemed permanent. Creatures knew where to find shade during the hottest parts of the day, where the most reliable water sources could be found, and how to time their reproduction with the brief seasonal rains. This stability, however, was deceptive. Deep beneath the surface, forces were building that would soon shatter this ancient equilibrium. Tectonic plates were shifting, ocean currents were beginning to change, and most ominously, Massive volcanic systems were stirring to life. The stage was being set for one of the most dramatic climate shifts in Earth's history. Though no living creature could have sensed what was coming, the transition began so subtly that at first, it might have seemed like nothing more than a particularly wet season. Perhaps the rains lasted a few weeks longer than usual, or the dry season was interrupted by unexpected storms. But as months passed, and then years, it became clear that something fundamental had changed in Earth's climate system. The catalyst for this transformation lay in a region that would one day become the Atlantic Ocean, but at the time was simply a massive zone of volcanic activity known as the Central Atlantic Magmatic Province. This wasn't ordinary volcanism, with isolated peaks occasionally erupting and then falling quiet. Instead, enormous fissures opened in the Earth's crust, releasing floods of lava that covered areas the size of modern countries. With the lava came gases, vast quantities of them, pumped into the atmosphere with each eruption. Carbon dioxide, the invisible driver of global warming, poured skyward in amounts that dwarf anything humans have ever produced. Sulfur compounds created aerosols that initially cooled the planet by reflecting sunlight back to space. But as the volcanic activity continued and intensified, the warming effects of the carbon dioxide began to dominate. The chemistry of the atmosphere was changing, and with it, the planet's entire weather system. Warmer air could hold more moisture, and as temperatures rose, evaporation from the oceans increased dramatically. More water vapor in the atmosphere meant more potential for precipitation, but it also meant more heat, trapped near Earth's surface, creating a feedback loop that pushed the climate toward increasingly extreme conditions. Ocean currents, those great conveyor belts that distribute heat around the globe, began to shift as temperature gradients changed. Monsoon patterns, which had brought seasonal rains to different parts of Pangaea, started to intensify and expand. What had once been predictable weather systems became erratic and powerful, driven by the additional energy in the atmosphere. The first signs of change would have been most noticeable in the tropical and subtropical regions of Pangaea. Areas that typically experienced distinct wet and dry seasons found their dry periods growing shorter and their wet seasons becoming more intense. Rivers that usually ran low during certain times of year remained swollen with runoff. Temporary lakes and wetlands that normally dried up during the hot season persisted, creating new habitats where none had existed before. As the volcanic activity continued, pumping more and more greenhouse gases into the atmosphere, these changes accelerated. The increased moisture in the air didn't just mean more frequent rain. It meant that when rain did fall, it came down harder and for longer periods. Storm systems that might once have lasted hours now persisted for days. Weather patterns that had been seasonal became year-round phenomena. For the plants and animals of this time, these changes represented both opportunity and crisis. Species that were already well adapted to wet conditions found themselves with expanded ranges and new territories to colonize. Amphibians, long restricted to the margins of the arid world, suddenly discovered vast new wetlands opening up across landscapes that had been desert for millions of years. But for the many species that had evolved in the dry world of early Pangaea, the increasing moisture presented serious challenges. Plants that had developed elaborate water conservation strategies found themselves overwhelmed by the abundance of moisture, their root systems struggling to cope with waterlogged soils. Animals that had evolved efficient kidneys and water retention abilities discovered that their adaptations were no longer advantages in a world where water was everywhere. The soil itself began to change as the rains continued. Hard-packed earth, baked by millions of years of sun and drought, started to soften and erode. Rivers carved deeper channels as increased rainfall fed them with more water than they had ever carried. Sediments that had remained stable for eons were suddenly mobilized, creating muddy torrents that reshaped the landscape with each storm. This was still just the beginning. The volcanic systems driving these changes showed no signs of slowing down, and the atmosphere continued to accumulate heat-trapping gases. What had started as unusually wet weather was evolving into something far more dramatic, something that would challenge every living thing on Earth to adapt or perish. As we'll discover, this was merely the opening act of a climate drama that would unfold over millions of years, fundamentally altering the trajectory of life on Earth. The gentle rains that marked the beginning of this transformation would soon become a deluge of unprecedented scale and duration, one that would drown entire ecosystems and force evolution itself to take new and unexpected paths. The world was about to learn what it meant when the sky refused to clear, when the concept of dry land became almost mythical, and when survival depended not on conserving water, but on learning to live in its endless abundance. And from this watery chaos would eventually emerge the ancestors of creatures that would one day rule the earth with thunder in their footsteps and ancient wisdom in their eyes. As the years stretched into decades and decades into centuries, the character of the rainfall itself began to change. What had started as intensified seasonal patterns evolved into something entirely unprecedented in Earth's history. The storms that now swept across Pangaea were unlike anything the planet had ever experienced, driven by atmospheric conditions that pushed the boundaries of what seemed physically possible. The sheer volume of water falling from the sky defied comprehension. Modern meteorologists would struggle to classify these ancient storm systems as they operated on scales that dwarf even the most extreme weather events of today. Imagine typhoons that never weakened, monsoons that never ended their season, and thunderstorms that rolled across continents for months without pause. The atmospheric river systems that developed during this time were truly colossal, carrying moisture from the vast Panthalassic Ocean deep into the heart of the supercontinent. These weren't the relatively narrow bands of water vapor that we know today, but massive corridors of saturated air that could span hundreds of miles in width. When these atmospheric rivers encountered mountain ranges or other topographic features, they would dump their cargo of moisture in torrential downpours that could last for weeks. But it wasn't just the intensity of individual storms that made this period so remarkable, it was their relentless persistence. The normal cycles that bring relief from wet weather, the high-pressure systems that clear skies and dry out the land, became increasingly rare. Instead, low-pressure systems dominated, creating a perpetual state of atmospheric instability that favored the formation of clouds and precipitation. The oceans themselves became engines of this endless moisture production. As global temperatures continued to rise due to the ongoing volcanic emissions, the surface waters grew warmer than they had been for millions of years. Warmer water evaporates more readily, and the increased evaporation fed more water vapor into an atmosphere that was already supersaturated with moisture. This created a feedback loop of staggering proportions. More evaporation led to more clouds, which led to more rain, which led to more warming as water vapor, itself a powerful greenhouse gas, trapped even more heat in the atmosphere. The planet had entered a climatic spiral that seemed to have no natural endpoint. A runaway greenhouse effect driven by the marriage of volcanic emissions and oceanic evaporation. The landscape began to transform in ways that would have seemed impossible just a few centuries earlier. Regions that had been arid for geological ages became vast wetlands almost overnight. Ancient lake beds that had been dry for millions of years suddenly filled with water and began to overflow, creating new river systems that carved fresh channels through terrain that had never known flowing water. The great deserts of early Pangaea, those vast expanses of sand and rock that had defined the supercontinent's interior, began to disappear beneath expanding networks of rivers, lakes, and marshes. Sand dunes that had stood for millennia were eroded away by the constant precipitation, their particles carried off by newly formed streams to be deposited in distant deltas and floodplains. Entire mountain ranges became shrouded in perpetual clouds, their peaks disappearing into grey veils that never lifted. The increased precipitation at high elevations created massive glaciers and ice fields, even in regions that had previously been too warm and dry to support permanent ice. These new ice masses began to carve valleys and reshape the mountain landscapes, adding another dimension to the planet's physical transformation. For the plants and animals struggling to survive in this new world, the changes came too fast for normal evolutionary processes to keep pace. Species that had thrived in the dry world found themselves marooned on shrinking islands of higher ground, watching as their traditional habitats disappeared beneath rising waters. Many simply couldn't adapt quickly enough and vanished from the fossil record, their extinction marking the end of evolutionary lineages that had persisted for millions of years. Yet life, with its remarkable resilience and creativity, began to find new ways to exploit these changed conditions. In the expanding wetlands, new communities of organisms began to flourish. Plants that had previously been confined to narrow strips along riverbanks suddenly found themselves with vast new territories to colonize. Ferns and other moisture-loving species spread rapidly across landscapes that had recently been barren desert. The animal communities of this waterlogged world were unlike anything that had existed before. Amphibians, freed from their previous constraints, diversified into forms that would seem alien to modern eyes. Some grew to enormous sizes, taking advantage of the abundant food resources in the new wetland ecosystems. Others developed specialized adaptations for life in permanently aquatic environments, beginning evolutionary journeys that would eventually lead to some of the most successful vertebrate lineages in Earth's history. The insects of this time period deserve special mention, as they too underwent dramatic changes in response to the new conditions. The high oxygen content of the atmosphere, combined with the warm, humid conditions, allowed some species to reach truly gigantic proportions. Dragonflies with wingspans measured in feet rather than inches patrolled the skies above the endless marshes, while enormous millipedes and other arthropods navigated the forest floors of the newly emerged wetland forests. But perhaps the most significant changes were occurring among the reptiles, particularly a group known as the archosaurs. These creatures, the ancestors of crocodiles, dinosaurs, and birds, found themselves uniquely positioned to take advantage of the New World Order. Their efficient respiratory systems, advanced circulatory systems, and sophisticated behavioral adaptations gave them advantages over their competitors in the challenging conditions of the waterlogged landscape. Some archosaur lineages began to develop semi-aquatic lifestyles, learning to hunt and breed in the extensive shallow water systems that now covered much of Pangaea. Others became specialized for life in the dense, humid forests that were springing up wherever the land remained above water level. These early experiments in aquatic and semi-terrestrial living would prove to be crucial stepping stones toward the eventual dominance of the dinosaur lineages. The changes weren't limited to terrestrial environments. The oceans themselves were being transformed by the massive influx of fresh water from the continents. River systems that had once carried modest seasonal flows now discharged enormous volumes of sediment-laden water into coastal areas. This changed the chemistry and clarity of nearshore waters, affecting marine ecosystems in ways that rippled through entire food webs. The increased erosion on land meant that vast quantities of nutrients were being washed into the oceans, creating conditions that favored explosive growth of marine algae and plankton. While this might seem beneficial, the reality was more complex. Algal blooms on such massive scales could deplete oxygen levels in the water when they died and decomposed, creating dead zones where marine life could not survive. These oceanic changes had their own feedback effects on the global climate system. Altered ocean currents, changed surface temperatures, and modified patterns of heat distribution all contributed to the atmospheric conditions that were driving the endless precipitation. The planet had become an interconnected system of climate feedback loops, each amplifying the others in ways that pushed Earth further from its previous state of relative stability. As the Carnian pluvial event continued to unfold, it became clear that this was not simply a period of unusual weather, but a fundamental reorganization of Earth's entire climate system. The world was being remade at the most basic level, from the composition of its atmosphere to the distribution of its landforms, from the chemistry of its oceans to the structure of its biological communities. And yet, even as the planet seemed to spiral into chaos, something remarkable was happening in the quieter corners of this transformed world. While the great reptilian dynasties of the Dry Age struggled to maintain their footing in the waterlogged landscape, smaller, more adaptable creatures were beginning to discover opportunities hidden within the catastrophe. The endless rains had created a world of micro-environments, each one slightly different from the next. A fallen log might remain dry enough on its underside to shelter creatures that couldn't tolerate the constant moisture, while its top surface became a garden of mosses and small plants. Rocky outcrops became islands of relative dryness in seas of mud and standing water, creating refuges where the old ways of life could persist, at least temporarily. In these pocket environments, evolution began to experiment with new solutions to the challenges of the waterlogged world. Some reptiles developed more efficient ways of shedding excess water from their scales. Others evolved behaviors that helped them navigate the treacherous terrain of mud and shifting ground. A few lineages began to show the first glimmers of adaptations that would later prove crucial for survival in aquatic environments. The plant communities were undergoing their own revolutionary changes. Species that had spent millions of years perfecting water conservation strategies suddenly found those adaptations to be burdens rather than advantages. Plants with thick, waxy leaves designed to minimize water loss discovered that these same features made it difficult for them to shed excess moisture, leading to problems with fungal infections and root rot. Meanwhile, plants that had previously been relegated to marginal habitats along streambeds and in seasonal wetlands suddenly found themselves in prime territory. Ferns, with their love of humid conditions, began to dominate landscapes where they had never been able to establish permanent populations. Tree ferns grew to enormous heights in the perpetually moist air, creating canopies that blocked sunlight from reaching the forest floor and fundamentally altering the structure of terrestrial ecosystems. The soil chemistry of this new world was unlike anything that had existed in Earth's previous history. The constant influx of water leached minerals from rocks at an accelerated pace, creating nutrient-rich runoff that fed into the expanding river systems. But this same process also stripped essential elements from many soils, creating nutrient-poor conditions in areas that had previously been fertile. The microbial communities that form the invisible foundation of all terrestrial ecosystems were forced to adapt to conditions of permanent saturation. Many species that had thrived in well-drained soils simply couldn't survive in the waterlogged conditions, while others that had been confined to permanently wet environments suddenly found vast new territories to colonize. These microscopic changes had cascading effects throughout the food web. Insects that depended on specific soil microorganisms for part of their life cycle found their reproduction disrupted. Plants that relied on particular fungal partnerships for nutrient uptake discovered that their symbionts couldn't survive in the altered soil conditions. Entire networks of ecological relationships that had taken millions of years to develop were unraveling in the space of just a few generations. But nature, as always, found ways to fill the vacant niches. New partnerships formed between species that had never previously interacted. Plants developed relationships with different fungal species that were better adapted to waterlogged conditions. Insects discovered new food sources among the plants and microorganisms that were thriving in the wet world. The atmospheric conditions during this time were truly extraordinary by any standard. The air itself had become a living thing, thick with moisture and alive with constant movement. Clouds formed and dissipated in endless cycles, but always more water was being added to the system than was being removed. The normal processes that clear the atmosphere, the high-pressure systems that bring dry air and sunny skies, had become rare visitors to most parts of Pangaea. Lightning became a near-constant presence in many regions, not just during traditional storm seasons, but throughout the year. The electrical activity in the atmosphere was intense enough to affect radio communications, had such technology existed at the time. The constant electrical discharge had its own effects on atmospheric chemistry, creating chemical reactions that wouldn't occur under normal conditions. The sound of this world would have been unlike anything we can imagine today. The constant patter of rain on leaves, the gurgle of water flowing over newly formed channels, the splash and bubble of marshes and wetlands, the distant rumble of thunder that never quite faded away. In many regions, the sound of flowing water became so constant that it formed a background noise that never ceased, a planetary soundtrack of liquid abundance. For animals that relied on sound for communication, hunting, or navigation, these acoustic changes presented significant challenges. Calls that had once carried clearly across dry landscapes were now muffled by the dense, humid air and masked by the omnipresent sound of falling and flowing water. Some species began to adapt by changing the frequency or volume of their vocalizations, while others shifted to different forms of communication entirely. The visual environment was equally transformed. The clear, harsh light that had characterized the arid world of early Pangaea gave way to a softer, more diffused illumination filtered through layers of clouds and mist. Many regions experienced a perpetual twilight, with full sunlight becoming a rare and precious commodity. This change in lighting conditions had profound effects on plant communities. Species that had evolved to thrive in intense, direct sunlight found themselves struggling in the dimmer conditions, while shade-tolerant plants that had previously been confined to the understory suddenly had opportunities to expand into new habitats. The reduced light levels also affected animal behavior in subtle but important ways. Many species that had been strictly diurnal found that the distinction between day and night became less meaningful in a world where the sky was often dark with clouds even at midday. Some began to adopt more flexible activity patterns, becoming active whenever conditions were favorable, rather than adhering to strict daily rhythms. Seasonal patterns, which had provided reliable cues for migration, reproduction, and other life cycle events, became increasingly unreliable. The traditional markers that animals used to time their activities, changes in day length, temperature fluctuations, and precipitation patterns, were all disrupted by the altered climate system. This temporal disruption had cascading effects throughout ecosystems. Plants that had evolved to flower at specific times of year found their pollinators arriving at the wrong time, or not at all. Predators that had timed their reproduction to coincide with abundant prey found that their usual food sources were no longer available when expected. Yet even in this chaos, life found ways to persist and even flourish. The key seemed to be flexibility, the ability to respond quickly to changing conditions rather than relying on rigid behavioral patterns. Species that could adjust their timing, their diet, their habitat preferences, or their social structures were more likely to thrive in the unpredictable world of endless rain. Among the most successful groups were those that had already been generalists, creatures that could eat a variety of foods, live in multiple habitat types, and tolerate a wide range of environmental conditions. These adaptable species found themselves with reduced competition as more specialized species struggled to cope with the changing world. The archosaurs, in particular, seemed to possess just the right combination of traits to take advantage of the new conditions. Their advanced respiratory systems allowed them to remain active in the oxygen-rich but humid air. Their relatively large brains gave them the behavioral flexibility to adapt to changing circumstances. And their efficient metabolism allowed them to make the most of food resources that might be scarce or unpredictable. As centuries turned to millennia, and millennia stretched toward millions of years, it became clear that the Carnian pluvial event was not a temporary disruption, but a fundamental shift in Earth's operating system. The planet had entered a new phase of its existence, one where water abundance rather than water scarcity was the defining characteristic of terrestrial life. This new world order would persist for an almost unimaginable span of time. long enough for entire evolutionary lineages to arise, flourish, and adapt to conditions that their ancestors could never have survived. It was a world that challenged every assumption about how life could organize itself, about what was possible in terms of climate and ecology, and about the resilience and creativity of evolution itself. And through it all, in ways both subtle and dramatic, the stage was being set for one of the most remarkable chapters in the history of life on Earth. The endless rains were not just transforming the present, they were creating the conditions that would allow entirely new forms of life to emerge and eventually dominate the planet in ways that would have seemed impossible in the dry world that had come before. The transformation of life during this endless deluge wasn't just about survival, it was about reinvention. As the rains continued their relentless symphony across the waterlogged world, something extraordinary began to emerge from the chaos. Evolution, that patient sculptor of life, had been handed new clay to work with, and it was creating forms that defied everything the dry world had taught about what was possible. In the shallow waters that now covered vast stretches of what had once been desert, entirely new ecosystems were taking shape. These weren't simply flooded versions of terrestrial habitats, but genuinely novel environments that bridged the gap between land and water in ways that had never existed before. Imagine vast, shallow seas dotted with islands of higher ground, connected by networks of channels and wetlands that shifted with each storm. The plants that colonized these amphibious landscapes developed remarkable adaptations. Some evolved hollow stems that could transport air to their roots, even when completely submerged. Others developed specialized structures that could function both as leaves in the air and as gills underwater, allowing them to photosynthesize regardless of the water level around them. These botanical pioneers were literally rewriting the rules of plant physiology. The most successful plant communities of this era were those that embraced the constant change, rather than fighting it. Floating forests developed, comprised of trees whose roots never touched solid ground, but instead formed vast mats that drifted with the currents. These living islands created their own microclimates, their canopies providing shelter for countless species, while their root systems filtered and purified the endless flow of water beneath them. Among the most remarkable developments were the emergence of what paleobotanists call amphiphytic plants, species that had evolved to thrive in the boundary zone between terrestrial and aquatic environments. These plants possess dual root systems, with some roots adapted for extracting nutrients from waterlogged soil, and others specialized for direct absorption from standing water. Their leaves showed similar versatility, with different sections optimized for aerial or submerged photosynthesis. The animal communities that evolved alongside these botanical innovations were equally extraordinary. In the endless marshes and wetlands, amphibians underwent what can only be described as an evolutionary explosion. Freed from the constraints that had confined them to the margins of the dry world, they diversified into forms that would challenge our modern understanding of what an amphibian could be. Some amphibian lineages grew to enormous sizes, becoming the apex predators of the wetland ecosystems. These creatures, some as large as modern crocodiles, developed powerful limbs and reinforced skulls that allowed them to hunt effectively, both in water and on the increasingly rare patches of dry land. Their skin became more sophisticated, developing specialized regions that could extract oxygen from water when submerged and from air when surfaced. Others took a different evolutionary path, becoming permanently aquatic, but retaining the lung-breathing capability that distinguished them from fish. These proto-aquatic amphibians developed streamlined bodies and powerful tails, becoming the first vertebrates to truly master the art of underwater flight through dense, plant-filled waters. But perhaps the most intriguing amphibian evolution occurred among species that learned to exploit the vertical dimension of the New World. With trees and tall plants constantly emerging from and disappearing beneath the fluctuating water levels, some amphibians developed enhanced climbing abilities and specialized toe pads that allowed them to navigate the three-dimensional maze of the flooded forests. The reptilian response to the endless rains was more complex and ultimately more significant for the future of life on Earth. While many of the great reptilian dynasties of the dry world struggled and eventually succumbed to the changed conditions, certain lineages found ways not just to survive, but to thrive in the waterlogged landscape. The early archosaurs, those ancestors of crocodiles and dinosaurs, proved particularly adept at navigating the challenges of the rain-soaked world. Their sophisticated cardiovascular systems, which had originally evolved for active hunting in arid environments, turned out to be perfectly suited for the oxygen-rich but physically demanding conditions of the wetlands. They could maintain high activity levels even when moving through dense vegetation or swimming through water-filled channels. More importantly, the archosaurs possessed behavioral flexibility that many other reptilian groups lacked. They were quick to exploit new food sources as ecosystems shifted around them. When traditional prey became scarce, they learned to hunt in the water. When terrestrial nesting sites disappeared beneath rising waters, they developed new reproductive strategies that took advantage of the floating vegetation mats. Some archosaur lineages began to develop what we might recognize as proto-crocodilian adaptations during this time. They elongated their skulls for more efficient aquatic hunting, developed more powerful tails for swimming, and evolved sensory systems that allowed them to detect prey movement in murky water. These weren't yet true crocodiles, but they were taking the first steps down evolutionary paths that would eventually lead to some of the most successful predators in Earth's history. Other archosaur groups took different approaches to the waterlogged world. Some developed enhanced terrestrial abilities, becoming more efficient at moving across the unstable, muddy surfaces that characterize much of the landscape. These creatures evolved broader feet for better weight distribution, stronger leg muscles for navigating difficult terrain, and enhanced balance systems for maintaining stability on shifting ground. The most remarkable archosaur adaptations, however, were occurring among the lineages that would eventually give rise to the dinosaurs. These early dinosauromorphs were developing a suite of characteristics that seemed almost tailor-made for the challenges of the rain-soaked world. Their upright posture allowed them to move efficiently through areas where other reptiles would bog down. Their advanced respiratory systems gave them endurance advantages in the humid, oxygen-rich atmosphere. Perhaps most significantly, these early dinosaur ancestors were developing enhanced metabolic systems that allowed them to maintain consistent activity levels despite the challenging environmental conditions. While many other reptiles became sluggish in the cool, humid conditions that often accompanied the endless storms, the dinosauromorphs remained active and alert, giving them crucial advantages in both hunting and avoiding predation. The marine environments during this time were experiencing their own dramatic transformations. The massive influx of fresh water from the continents was creating conditions unlike anything that had existed in Earth's oceans before. Vast plumes of sediment-laden river water extended far out to sea, creating unique brackish environments that supported their own specialized communities of organisms. In these transitional marine environments, new forms of life were experimenting with adaptations that blurred the lines between freshwater and saltwater existence. Some marine reptiles developed enhanced kidney functions that allowed them to process the variable salinity levels they encountered as they moved between different water masses. Others evolved specialized glands that could excrete excess salt when in marine conditions or retain essential minerals when in fresher water. The most significant marine developments were occurring among the early marine reptiles that were beginning to explore fully aquatic lifestyles. The abundant food resources created by nutrient runoff from the continents supported larger populations of marine organisms than had existed in previous eras. This abundance allowed some reptilian lineages to make the complete transition from semi-aquatic to fully marine existence. These early marine reptiles were developing the streamlined body forms, powerful swimming appendages, and specialized sensory systems that would characterize successful marine predators for millions of years to come. Some evolved echolocation abilities to navigate in the often murky coastal waters. Others developed enhanced visual systems that could function in the variable, effectively light conditions created by the massive algal blooms that were becoming common in nutrient-rich coastal areas. The atmospheric chemistry during this extended period was creating conditions that modern life would find almost unimaginable. The constant evaporation and precipitation was cycling vast quantities of water through the atmosphere, but it was also mobilizing other chemicals in unprecedented ways. Volcanic gases continued to be released, but now they were being processed through atmospheric systems that were fundamentally different from those of the dry world. The high humidity levels meant that many chemical reactions that would normally occur slowly were accelerated. The atmosphere itself became a kind of chemical reactor, with constant electrical activity from storms driving reactions that created new compounds and broke down others. Some of these atmospheric chemical processes began to have effects on the evolution of life itself, as organisms were exposed to novel chemical environments that selected for new types of biochemical resilience. The soil chemistry of the rain-soaked world was equally dynamic. The constant movement of water was creating complex patterns of nutrient distribution that changed from season to season and year to year. Plants that could adapt quickly to changing soil conditions had enormous advantages over those that required stable chemical environments. Some plant lineages began to develop what we might call chemical flexibility, the ability to alter their metabolic processes based on the available nutrients in their immediate environment. These plants could switch between different photosynthetic pathways, activate alternative nutrient uptake mechanisms, or even change their growth patterns based on the chemistry of the water and soil around them. The microbial communities that formed the foundation of these new ecosystems were perhaps the most dynamic element of all. Bacteria and other microorganisms that could thrive in waterlogged conditions found themselves with virtually unlimited territory to colonize. They formed complex biofilms that covered submerged surfaces, created floating mats that provided structure in open water areas, and developed symbiotic relationships with larger organisms that were struggling to adapt to the new conditions. These microbial communities became essential partners for many of the plants and animals that successfully colonized the waterlogged landscapes. They helped break down organic matter in oxygen-poor sediments, fix nitrogen from the atmosphere in forms that plants could use, and even provided essential vitamins and other compounds that were difficult to obtain in the altered chemical environment. The insect world during this time was undergoing its own remarkable transformation. The high oxygen levels and warm, humid conditions created an environment where arthropods could achieve sizes that would be impossible under modern atmospheric conditions. But size wasn't the only change. These insects were also developing new ecological roles that had never existed before. Some insects evolved to become aquatic as adults, developing gills and other adaptations that allowed them to spend their entire life cycles underwater. Others became specialists at exploiting the boundary zones between terrestrial and aquatic environments, developing the ability to walk on water surfaces or to dive beneath the surface to escape predators or find food. The most remarkable insect adaptations were occurring among species that learned to exploit the vertical complexity of the flooded forests. These insects developed enhanced flight capabilities that allowed them to navigate through the dense three-dimensional maze of branches, vines, and floating vegetation. Some evolved the ability to hover like modern hummingbirds, allowing them to feed on nectar or hunt for prey while remaining stationary in midair. As millions of years passed and the endless rains continued, the world that emerged was so different from what had come before that it might as well have been an alien planet. This was a world where the concept of truly dry land had become almost mythical, where life had learned to thrive in conditions of perpetual abundance rather than scarcity, and where evolution had been forced to explore entirely new solutions to the fundamental challenges of existence. The creatures that inherited this transformed world were unlike anything that had existed in Earth's previous history. They were the products of an evolutionary experiment conducted on a planetary scale, shaped by conditions that pushed life to explore possibilities that had never before been available. And among these remarkable creatures, certain lineages were beginning to show the first signs of characteristics that would eventually allow them to dominate not just the waterlogged landscapes of their time, but the entire planet for millions of years to come. In the quiet backwaters and hidden channels of this drowned world, small bipedal reptiles were learning to run upright through shallow water, their long tails providing balance as they navigated the treacherous terrain. Their keen eyes scanned the misty horizons for opportunities, while their efficient lungs processed the oxygen-rich air with remarkable effectiveness. They were still small, still cautious, still overshadowed by the giants of their age. But they were learning, adapting, surviving. And in the endless rains that had reshaped their world, they were discovering capabilities that would one day shake the earth itself. The endless deluge was reshaping more than just landscapes and ecosystems. It was rewriting the very rules of survival, creating pressures that would forge evolutionary innovations unlike anything the planet had ever witnessed. As the rains continued their relentless rhythm across the transformed world, something profound was happening in the hidden corners of this aquatic realm. Life wasn't just adapting to the water, it was learning to harness its power. Deep within the flooded forests, where ancient tree trunks stood like cathedral pillars rising from dark mirrors of standing water, a revolution was taking place at the molecular level. The constant saturation wasn't merely a challenge to overcome, it was becoming the driving force behind entirely new forms of biological innovation. Plants were developing internal transportation systems that could function like hydraulic networks, using water pressure to move nutrients and chemical signals throughout their structures with unprecedented efficiency. Some of the most remarkable adaptations were emerging among the flowering plants, though they were still primitive compared to the botanical marvels that would eventually carpet the earth. These early angiosperms were experimenting with reproductive strategies that took advantage of the water-dominated environment. Instead of relying solely on wind or insect pollination, some species developed seeds that could float for months without losing viability, allowing them to colonize distant habitats as they drifted along the endless network of waterways. The chemistry of reproduction itself was being transformed by the aquatic environment. Pollen grains evolved waxy coatings that protected them during long journeys through humid air and standing water. Some plants developed the ability to release their genetic material directly into the water, where it could travel vast distances before finding receptive partners. This aquatic reproduction created genetic mixing on a scale that had never been possible in the fragmented dry world of earlier eras. But perhaps the most extraordinary botanical development was the emergence of what researchers now call living bridges. These were plants that grew in specific patterns, their roots and stems interweaving to create stable platforms that could support entire communities of smaller organisms. These biological structures formed natural highways through the flooded landscape, allowing animals to move between areas of higher ground without having to swim through open water. The animal communities that developed around these living bridges were unlike anything that had existed before. Small mammals, still rare and primitive compared to their later descendants, found refuge in the hollow stems and root chambers of the bridge plants. These tiny creatures were learning to exploit three-dimensional space in ways their terrestrial ancestors never could, developing enhanced climbing abilities and spatial awareness that would prove crucial for their eventual evolutionary success. Among the most successful bridge dwellers were early primates and their relatives, creatures whose grasping hands and keen intelligence made them perfectly suited for navigating the complex architecture of the living structures. These animals were developing social behaviors that revolved around the maintenance and protection of their plant hosts, forming some of the first truly mutualistic relationships between mammals and flowering plants. The reptilian inhabitants of this waterlogged world were undergoing even more dramatic transformations. The endless abundance of water had eliminated one of the primary constraints that had shaped reptilian evolution throughout their history: the need to conserve moisture. Freed from this ancient limitation, reptilian physiology began to explore entirely new possibilities. Some lineages developed what can only be described as internal climate control systems. These reptiles evolved specialized blood vessels that could redirect circulation based on environmental conditions, allowing them to maintain optimal body temperature even when moving between warm, sunlit areas and cool, shaded waters. Their scales became more sophisticated, developing microscopic structures that could trap air for insulation when dry or shed water efficiently when wet. The most remarkable reptilian innovation was the development of what paleontologists call adaptive metabolism. These creatures could literally change their metabolic rate based on available resources and environmental conditions. During periods of abundance, they could accelerate their metabolism to take advantage of plentiful food and ideal growth conditions. When resources became scarce or conditions challenging, they could slow their metabolism to conserve energy, entering states of reduced activity that allowed them to survive extended periods of hardship. This metabolic flexibility was particularly pronounced among the early dinosauromorph lineages. These creatures were developing internal systems that would eventually allow them to maintain consistent activity levels across a much wider range of environmental conditions than any reptile had ever achieved. Their hearts were becoming more efficient, their lungs more sophisticated, their digestive systems more versatile. The neural development occurring among these early dinosaur ancestors was equally remarkable. The complex, ever-changing environment of the flooded world placed a premium on behavioral flexibility and problem-solving ability. Creatures that could quickly assess new situations, adapt their behavior to changing circumstances, and learn from experience had enormous advantages over those that relied on fixed behavioral patterns. Brain structures that processed spatial information became more sophisticated, as animals needed to navigate three-dimensional environments that were constantly shifting with water levels and seasonal changes. Memory systems evolved to handle more complex information, as creatures needed to remember the locations of resources that might only be accessible under specific conditions. Social behaviors also became more complex during this time. The patchy distribution of habitable areas in the flooded landscape meant that when animals did encounter others of their species, these meetings took on heightened significance. Cooperation in finding food, sharing information about safe travel routes, and coordinating care of young became essential survival strategies. Some reptilian lineages began to develop rudimentary forms of communication that went beyond simple territorial displays. These creatures evolved the ability to convey information about distant resources, warn of dangers in specific locations, and coordinate group movements through dangerous terrain. The foundations of what would eventually become sophisticated social intelligence were being laid in the mist-shrouded channels of the drowned world. The marine environments during this extended period were experiencing their own parallel freshwater and saltwater hay revolution. The boundary between became increasingly blurred, creating vast estuarine systems that supported unique communities of organisms adapted to variable salinity conditions. These transitional environments became evolutionary laboratories where aquatic life experimented with new forms and functions. Marine reptiles were developing increasingly sophisticated adaptations for fully aquatic life. Their limbs were becoming more paddle-like, their bodies more streamlined, their sensory systems more attuned to underwater conditions. Some lineages evolved echolocation abilities that allowed them to navigate and hunt in the murky waters created by constant sediment runoff from the continents. The most significant marine development was the emergence of what paleontologists call ecosystem engineers among the marine reptiles. These creatures actively modified their environment to create more favorable conditions for themselves and their prey. Some species learned to create artificial reefs by manipulating floating debris and sediment. Others developed the ability to modify water chemistry through their metabolic processes, creating localized areas with optimal conditions for feeding or reproduction. These ecosystem engineers had cascading effects throughout the marine food web. Their activities created new habitats that supported diverse communities of smaller organisms, which in turn attracted different predators and created more complex ecological relationships. The oceans were becoming more structured, more layered, with different communities occupying specific niches within the larger aquatic environment. The atmospheric conditions during this time continued to drive changes that affected every aspect of life on Earth. The constant cycling of water through evaporation and precipitation was creating weather patterns of extraordinary complexity and power. Storm systems that would dwarf any modern hurricane became routine features of the global climate, moving vast amounts of energy and moisture around the planet in cycles that lasted for decades or centuries. These superstorms weren't merely destructive forces. They were also agents of biological dispersal on an unprecedented scale. Seeds, spores, small animals, and even larger creatures could be transported across vast distances by the powerful wind and water currents associated with these massive weather systems. This long-distance dispersal was accelerating evolution by bringing together species that might never have encountered each other under normal circumstances. The mixing of populations that occurred during these storm-driven dispersal events created opportunities for genetic exchange between previously isolated groups. New hybrid forms emerged, some of which proved better adapted to the changing conditions than either of their parent species. Evolution was being accelerated by the very forces that seemed to be creating chaos in the natural world. The electrical activity associated with the constant storms was having its own effects on evolutionary processes. The intense electromagnetic fields generated by lightning could cause genetic mutations at rates higher than normal background levels. Most of these mutations were harmful or neutral, but some provided advantages that were quickly selected for in the rapidly changing environment. Some organisms even began to evolve sensitivity to electrical fields, allowing them to detect approaching storms, navigate using the Earth's magnetic field, or communicate using bioelectric signals. These electrical senses would eventually prove crucial for many lineages, providing them with information about their environment that was unavailable through conventional senses. The soil ecosystems of this waterlogged world were developing their own unique characteristics. The constant moisture created conditions where decomposition occurred much more rapidly than in dry environments, leading to extremely rich organic soils in many areas. These fertile sediments supported plant communities of unprecedented density and diversity. However, the rapid decomposition also created challenges. Nutrients that would normally be released slowly over time were instead made available in sudden pulses that could overwhelm plant systems. Some plant lineages evolved the ability to store excess nutrients in specialized organs, allowing them to survive periods when nutrient availability dropped below normal levels. The microbial communities in these waterlogged soils were incredibly diverse and active. Bacteria and fungi that could process organic matter under low oxygen conditions became dominant, creating complex biochemical cycles that processed materials in ways that had never occurred in dry soils. These microorganisms formed partnerships with plant roots that were far more sophisticated than simple nutrient exchange, involving complex chemical communication systems that allowed plants and microbes to coordinate their activities. Some of the most remarkable soil organisms were anaerobic bacteria that could derive energy from chemical processes rather than photosynthesis. These creatures created localized chemical environments that were completely different from the surrounding soil, forming microhabitats that supported their own unique communities of organisms. The insect communities of this era were reaching new heights of diversity and specialization. The three-dimensional complexity of the flooded forests, combined with the rich chemical environment created by the diverse plant communities, provided insects with more ecological niches than had ever existed before. Some insects became specialists at exploiting specific parts of the water-plant interface, developing adaptations that allowed them to feed on submerged roots, floating leaves, or the complex biofilms that covered most underwater surfaces. Flight capabilities reached new levels of sophistication as insects adapted to navigate through the dense, humid air of the flooded forests. Some species developed the ability to fly underwater for short distances, using their wings as propulsion systems in the dense medium. Others evolved specialized flight patterns that allowed them to hover motionlessly in specific locations, waiting for prey or mates to appear. The most remarkable insect evolution was occurring among species that developed life cycles specifically adapted to the fluctuating water levels that characterized most habitats. These insects could time their reproduction to coincide with optimal water conditions, ensuring that their offspring would emerge into environments that provided the best chances for survival. Some insect lineages even began to influence the hydrology of their local environments. Certain species learned to construct dams and channels that modified water flow patterns, creating more stable conditions for their own reproduction and development. These insect engineers were among the first animals to actively manage their water resources, a capability that would prove increasingly important as the climate continued to evolve. The vertebrate communities that emerged from this extended period of aquatic dominance were fundamentally different from anything that had existed in the dry world. These creatures had been shaped by millions of years of life in an environment where water was not just abundant, but omnipresent, where the ability to thrive in aquatic conditions was often the difference between success and extinction. Among the most successful vertebrates were those that had learned to exploit the boundary zones between different aquatic environments. These creatures could move seamlessly between shallow wetlands, deeper channels, and the occasional patches of temporarily dry ground, taking advantage of resources and avoiding dangers across the full spectrum of available habitats. The early dinosauromorph lineages were proving particularly adept at this multi-habitat lifestyle. Their efficient cardiovascular systems, sophisticated respiratory adaptations, and enhanced neural capabilities gave them advantages in almost every environment they encountered. They were becoming the consummate generalists of their age, capable of thriving wherever conditions allowed vertebrate life to persist. But these creatures were more than just successful survivors. They were developing capabilities that would eventually allow them to reshape entire ecosystems according to their own needs. Their intelligence was growing, their social behaviors becoming more complex, their physical abilities more refined with each passing generation. In the misty dawns of this waterlogged world, as the endless rains continued to fall and the flooded landscapes stretched to every horizon, these small but remarkable creatures were taking the first steps toward a destiny that would eventually carry them far beyond the aquatic realm of their birth. They were learning to think, to plan, to dream of possibilities that extended beyond the endless cycle of rain and flood that had defined their world for so long. The stage was being set for the next great chapter in Earth's story, though it would be millions of years before the curtain would finally rise on that grander drama. For now, in the gentle patter of eternal rainfall and the soft splash of creatures moving through shallow channels, the future was taking shape in ways both subtle and profound, preparing for transformations that would one day echo across the entire planet with the thunder of footsteps and the roar of voices that had not yet learned to speak. As the endless centuries of rain continued to reshape the world, something remarkable was happening beneath the surface of this transformed planet. The very foundation of life itself was being rewritten, not just in the bodies of individual creatures, but in the fundamental relationships that connected all living things together. The waterlogged world had become a vast laboratory, where evolution was conducting experiments on a scale that defied imagination. In the deeper channels that now carved through landscapes once dominated by desert sands, entirely new forms of predation were evolving. The constant flow of nutrient-rich water had created feeding opportunities that simply hadn't existed in the dry world. And creatures were developing hunting strategies that took advantage of these liquid highways. Some early archosaurs learned to position themselves at the convergence points where multiple channels met, using the water currents to bring prey directly to them in a kind of passive hunting that required minimal energy expenditure. These aquatic ambush predators were developing sensory capabilities that bordered on the supernatural by the standards of their dry world ancestors. They could detect the slightest vibrations in the water, feel the pressure waves created by swimming prey from remarkable distances, and even sense the electrical fields generated by the muscle contractions of other animals. Their skulls were elongating and flattening, creating hydrodynamic shapes that allowed them to strike with lightning speed through the dense medium of water. But perhaps most remarkably, some of these aquatic hunters were beginning to develop what can only be described as tactical intelligence. They weren't simply reacting to prey that happened to swim within range. They were actively manipulating their environment to increase their hunting success. Some learned to create artificial currents by positioning themselves in specific ways, herding schools of fish into confined areas where escape was impossible. Others developed the ability to work in coordinated groups, with different individuals taking on specialized roles in complex hunting strategies. The plant communities that formed the foundation of these aquatic ecosystems were themselves becoming more animal-like in their behaviors. Some species developed the ability to actively capture and digest small organisms, supplementing their photosynthetic nutrition with protein obtained directly from prey. These carnivorous plants weren't passive trap setters like their modern descendants, but active hunters that could move their specialized feeding structures to pursue swimming prey through the water column. Even more extraordinary were the plants that learned to form partnerships with animal species in relationships that went far beyond simple pollination or seed dispersal. Some flowering plants developed specialized chambers within their stems and roots that provided shelter for small vertebrates in exchange for protection and nutrient-rich waste products. These plant-animal partnerships created living structures that were more resilient and adaptable than either partner could have been on its own. The most sophisticated of these relationships involved plants that actually modified their growth patterns based on the needs of their animal partners. They could strengthen certain branches to support heavier animals, create new chambers as populations grew, or even alter their chemical defenses to provide better protection for their residents. These weren't simple mutualisms, but genuine partnerships where both species actively contributed to shared goals. In the vast wetland systems that now covered much of what had once been Pangaea's interior, new forms of social organization were emerging among vertebrate species. The patchy distribution of resources in the aquatic landscape favored animals that could share information about food sources, safe travel routes, and seasonal changes in water levels. Some early reptilian lineages developed communication systems sophisticated enough to convey complex spatial information, allowing group members to coordinate their activities across distances that spanned multiple watersheds. These communication networks weren't limited to members of the same species. Different types of animals began to develop interspecies communication protocols, creating information-sharing alliances that benefited all participants. A bird might signal the location of a rich feeding area to a group of semi-aquatic reptiles, which in turn might warn the bird of approaching predators. These cross-species partnerships were laying the groundwork for ecosystem-level cooperation that would prove crucial for survival in an increasingly complex world. The respiratory innovations occurring during this time were particularly remarkable among the reptilian lineages that would eventually give rise to dinosaurs. These creatures were developing breathing systems that could extract oxygen efficiently from both air and water, allowing them to remain active in environments where oxygen levels fluctuated dramatically. Their lung structures were becoming more complex, with specialized chambers that could function differently depending on the medium they were processing. Some of these early dinosaur-amorph lineages even developed the ability to store oxygen in their blood and tissues for extended periods, allowing them to remain underwater far longer than should have been possible for air-breathing animals. This adaptation proved crucial for exploiting food resources in deep water environments and for escaping terrestrial predators by diving into channels and remaining submerged until danger passed. The skeletal adaptations occurring among these creatures were equally impressive. Bones were becoming lighter but stronger, with internal structures that provided maximum strength with minimal weight. This was particularly important for animals that needed to be buoyant in water, but also capable of rapid movement on land. Some species developed hollow bones filled with air spaces that not only reduced their weight, but also provided additional oxygen storage for extended underwater activities. The muscular systems of these animals were becoming incredibly efficient, with specialized muscle groups for aquatic locomotion and others optimized for terrestrial movement. The transition between swimming and walking was becoming so seamless that some creatures could literally run across the surface of shallow water, using surface tension and rapid leg movements to maintain their position above the waterline. Neural development was accelerating at an unprecedented rate among the vertebrates of this aquatic age. The complex, three-dimensional environment of the flooded world required spatial processing capabilities far beyond anything that had been necessary in the relatively simple, terrestrial environments of the dry world. Brain structures dedicated to navigation, memory, and problem-solving were expanding rapidly, creating cognitive capabilities that approached those of much later, more famous species. Some of the most remarkable neural adaptations were occurring in the sensory processing centers of these early brains. Animals were developing the ability to create detailed mental maps of their three-dimensional aquatic territories, keeping track of seasonal changes in water levels, the locations of temporary islands, and the movements of both prey and predators through complex channel systems that could span hundreds of square miles. The social implications of these enhanced cognitive abilities were profound. Animals that could remember and communicate complex information about their environment were able to form larger, more stable social groups than had ever existed before. These groups could coordinate their activities across vast areas, sharing resources and information in ways that benefited all members. Some reptilian lineages began to develop what can only be described as cultural transmission of knowledge. Older, more experienced individuals would teach younger members of the group about navigation routes, seasonal patterns, and survival strategies. This cultural learning accelerated the adaptation process, allowing groups to respond to environmental changes much more quickly than would have been possible through genetic adaptation alone. The reproductive strategies that evolved during this period were as innovative as any other aspect of life in the waterlogged world. Many species developed extended parental care systems, with adults protecting and teaching their offspring for much longer periods than had been typical in the dry world. This extended childhood allowed young animals to learn the complex skills necessary for survival in their challenging environment. Some species even developed cooperative breeding systems, where multiple adults would contribute to raising the young of the group. These cooperative systems created strong social bonds and allowed for the transmission of knowledge and skills across generations. The young animals that grew up in these cooperative groups developed enhanced social intelligence and problem-solving abilities that served them well throughout their lives. The metabolic innovations occurring during this time were setting the stage for one of the most important developments in vertebrate evolution. Some reptilian lineages were beginning to develop the ability to maintain consistent internal body temperatures regardless of environmental conditions. This wasn't yet the full warm-blooded metabolism that would later characterize mammals and birds, but it was a crucial direction. These step in that proto-endothermic adaptations allowed certain species to remain active during the cool, cloudy periods that were common in the rain-dominated climate. While other reptiles became sluggish in the reduced sunlight and lower temperatures, these metabolically advanced creatures could continue hunting, socializing, and reproducing regardless of weather conditions. The advantages of metabolic independence were enormous in the unpredictable climate of the endless rains. Animals that could maintain their activity levels during storms, temperature drops, or extended cloudy periods had access to resources and opportunities that were unavailable to their cold-blooded competitors. This metabolic flexibility was becoming one of the most important factors determining success or failure in the transformed world. The chemical communication systems that evolved during this period were incredibly sophisticated. The high humidity and constant water movement created ideal conditions for the transmission of chemical signals over long distances. Some species developed the ability to release specific molecules into the water that could carry detailed information about their identity, reproductive status, territorial boundaries, and even emotional states. These chemical messages could persist in the water for extended periods, creating a kind of chemical landscape that animals could read like a map. Creatures could determine who had passed through an area, when they had been there, and what they had been doing, all by analyzing the chemical traces left behind in the water. The most advanced chemical communication systems allowed for real-time conversations between individuals separated by considerable distances. Animals could release sequences of different molecules that conveyed complex information, and recipients could respond with their own chemical messages, creating chemical dialogues that could continue for hours or even days. The electromagnetic sensitivities that some species developed during this time provided yet another dimension to their environmental awareness. The constant electrical activity in the storm-filled atmosphere created electromagnetic fields that could be detected and interpreted by animals with the appropriate sensory organs. Some creatures learned to use these electromagnetic cues for navigation, allowing them to maintain their orientation even in the murky, low-visibility conditions that were common in the flooded landscape. Others developed the ability to detect the bioelectric fields generated by other animals, giving them almost supernatural abilities to locate hidden prey or detect the approach of predators. These electromagnetic sensors were particularly useful in aquatic environments, where traditional senses like sight and hearing were often limited by water conditions. As the millennia passed and the endless rains continued to fall, the world that had emerged from this aquatic transformation was becoming something that would have been utterly unrecognizable to the creatures that had inhabited the dry world of earlier eras. This wasn't simply a matter of different species occupying familiar ecological roles. The very concept of what it meant to be alive on Earth had been fundamentally altered. The boundaries between different types of environments had become fluid, both literally and figuratively. Terrestrial, freshwater, and marine ecosystems were blending together in complex gradients that created entirely new categories of habitat. Animals and plants were developing the flexibility to thrive across these environmental gradients, leading to life forms that defied traditional classification schemes. The concept of seasonal cycles had been completely transformed by the endless precipitation. Instead of the predictable alternation between wet and dry seasons that had characterized the pre-rain world, life now operated according to more complex rhythms based on storm intensity, water temperature, and the availability of different types of aquatic habitats. Some species developed life cycles that could span multiple years, allowing them to take advantage of rare optimal conditions when they occurred. The food webs that supported life in this transformed world were more complex and interconnected than anything that had existed before. The constant movement of water created connections between distant ecosystems, allowing nutrients and organisms to flow between areas that would have been completely isolated in a terrestrial environment. This connectivity meant that changes in one part of the system could have effects that rippled across entire continents. The energy flows through these aquatic ecosystems were incredibly efficient, with multiple levels of recycling and reuse that minimized waste and maximized productivity. Decomposer organisms had become highly specialized for processing organic matter in waterlogged conditions, creating nutrient cycles that could support much higher population densities than had been possible in dry environments. The evolutionary pressures operating in this waterlogged world were creating selection forces unlike anything that had existed in Earth's previous history. The ability to process information quickly, adapt to changing conditions, and cooperate with other organisms was becoming more important for survival than traditional factors like size, strength, or defensive capabilities. Intelligence was becoming the ultimate survival tool, and the creatures that were developing the most sophisticated cognitive abilities were beginning to dominate their ecosystems in ways that went beyond simple predation or resource competition. These animals were becoming ecosystem managers, actively modifying their environments to create conditions that favored their own survival and reproduction. Among the most successful of these intelligent survivors were the small, bipedal archosaurs that had learned to exploit the three-dimensional complexity of the flooded forests. Their enhanced cognitive abilities, efficient metabolisms, and social cooperation were giving them advantages that extended far beyond their modest size. They were learning to think strategically, to plan for future needs, and to work together in ways that multiplied their individual capabilities. These creatures were still small, still vulnerable to the larger predators that roamed the waterlogged landscapes. But they possessed something that their competitors lacked: the ability to envision possibilities that extended beyond their immediate circumstances. In the misty channels and rain-soaked forests of their aquatic world, they were developing the intellectual and social foundations that would one day allow their descendants to inherit not just the transformed landscapes of their time, but the entire planet. The endless rains continued to fall as they had for millions of years, drumming their liquid rhythm against leaves that had never known true dryness, flowing through channels that carried the dreams and ambitions of creatures still learning what it meant to think beyond the moment. In the depths of this aquatic age, evolution was preparing its most audacious experiment yet, though the results would not be revealed for millions of years to come. The future was taking shape in the gentle splash of small feet moving through shallow water, in the quiet conversations of creatures sharing knowledge across the misty distances, in the patient observations of eyes that were learning to see patterns in the chaos of their endlessly changing world. The rain of water would not last forever, but the lessons learned in its liquid embrace would echo through time, shaping destinies that reached far beyond the rain-soaked horizons of that ancient drowned earth. But even as life flourished in these aquatic realms, the forces that had created this waterlogged world were beginning to shift once again. Deep beneath the surface, the volcanic systems that had pumped greenhouse gases into the atmosphere for millions of years were entering a new phase of their existence. The massive eruptions that had sustained the endless rains were starting to change their character, releasing different combinations of gases that would gradually alter the delicate balance that had maintained the planet's hydrological cycle. The chemistry of the atmosphere began to evolve in subtle but significant ways. While carbon dioxide levels remained high, other compounds were being introduced that would interact with water vapor in unexpected ways. Sulfur compounds, released in different proportions than before, began to form aerosol particles that reflected more sunlight back to space. These tiny particles, invisible to the creatures below, started to create a cooling effect that competed with the warming influence of the greenhouse gases. Ocean currents, those vast rivers of water that had carried heat and moisture around the globe for so long, began to respond to changing temperature gradients. The poles, which had remained relatively warm during the height of the endless rains, started to cool as the atmospheric chemistry shifted. This cooling created new patterns of air circulation that gradually began to disrupt the storm systems that had dominated the planet's weather for so long. The first signs of change were subtle, noticed only by the most sensitive organisms that had learned to read the complex environmental signals of their aquatic world. Storm systems that had once persisted for months began to show brief intervals of calm. Cloud formations that had maintained their structure for years started to dissipate more quickly. The rhythm of the endless precipitation began to develop pauses, moments of respite that grew longer with each passing century. For the creatures that had evolved in the waterlogged world, these changes represented both opportunity and crisis. Species that had become completely dependent on aquatic environments found themselves facing the terrifying possibility that their liquid realm might not be permanent. The vast wetland systems that had supported incredible biodiversity began to experience fluctuations in water level that exposed previously submerged areas to open air. Plants that had never experienced true drought found themselves struggling to survive as water levels dropped and the intervals between rainfall grew longer. Some species possessed enough genetic flexibility to adapt quickly to the changing conditions, developing more efficient water conservation systems or deeper root structures that could tap into groundwater reserves. Others, particularly those that had become highly specialized for fully aquatic lifestyles, began to decline as their specialized habitats shrank. The animal communities faced equally challenging transitions. Fully aquatic species found themselves confined to deeper channels and permanent water bodies as the extensive shallow water systems began to dry up. Competition for these remaining aquatic refuges intensified, leading to conflicts between species that had coexisted peacefully when water was abundant everywhere. However, for the creatures that had maintained some flexibility in their habitat requirements, the changing conditions presented unprecedented opportunities. The early dinosauromorph lineages, with their efficient metabolisms and adaptable behaviors, found themselves uniquely positioned to exploit the expanding areas of exposed land. Their ability to function effectively in both aquatic and terrestrial environments became an enormous advantage as the world began its gradual transition away from complete aquatic dominance. These adaptable species began to expand their ranges rapidly, colonizing newly exposed territories that had been underwater for millions of years. The soils in these areas were incredibly rich, having been continuously fertilized by the organic matter that had accumulated during the long aquatic period. Plants that could tolerate the changing moisture conditions established themselves quickly, creating new terrestrial ecosystems that were more productive than anything that had existed in the pre-rain world. The exposed lakebeds and dried river channels revealed landscapes that were unlike anything in Earth's previous history. Centuries of sediment deposition had created incredibly flat, fertile plains that stretched for hundreds of miles without significant topographic relief. These vast flatlands became ideal habitats for animals that could move efficiently across open terrain, and the early dinosauromorph lineages were among the first to take advantage of these new opportunities. Their bipedal locomotion, which had originally evolved for moving through shallow water and dense vegetation, proved to be perfectly suited for rapid travel across the open plains. Their enhanced cardiovascular systems allowed them to maintain high activity levels during long-distance movements, while their sophisticated respiratory adaptations enabled them to process the changing atmospheric chemistry more efficiently than their competitors. The social behaviors that had developed during the aquatic age became even more important as these creatures expanded into new territories. The ability to communicate complex information about distant resources, coordinate group movements across vast distances, and share knowledge about environmental conditions gave them decisive advantages in colonizing the emerging landscapes. Some groups began to develop what could only be described as exploratory behavior, sending small parties of individuals to investigate distant areas and report back on conditions, resources, and potential threats. This systematic exploration allowed them to identify the most promising new territories and plan their expansion strategies accordingly. The cognitive abilities that had been honed during millions of years of navigating complex aquatic environments proved invaluable for understanding and exploiting terrestrial landscapes. These creatures could analyze topographic features, predict seasonal changes in resource availability, and develop mental maps of vast territories that enabled them to navigate confidently across unfamiliar terrain. As the climate continued its gradual transition away from the endless rains, seasonal patterns began to emerge for the first time in millions of years. The concept of predictable wet and dry periods, which had been absent during the aquatic age, slowly returned to influence the rhythms of life. Species that could anticipate and prepare for these seasonal changes gained significant advantages over those that remained reactive to immediate environmental conditions. The early dinosauromorph lineages demonstrated remarkable abilities to predict and plan for seasonal variations. They developed food storage behaviors, created shelter systems that could protect them during adverse weather, and timed their reproductive activities to coincide with optimal environmental conditions. These planning capabilities represented a level of cognitive sophistication that far exceeded anything that had existed in the pre-rain world. The transition period also witnessed the emergence of increasingly complex territorial behaviors. As water became less universally abundant, control of reliable water sources became a crucial factor in survival. Some species developed sophisticated territorial marking systems and established complex social hierarchies based on access to prime real estate rather than simple physical dominance. The most successful territorial systems were those that balanced individual needs with group cooperation. Species that could maintain cohesive social groups while also defending valuable resources from outsiders found themselves able to control larger territories and access more diverse resources than solitary species or those with purely competitive social structures. The plant communities that emerged during this transition period were remarkable for their rapid diversification and adaptation. Having evolved during millions of years of constant moisture, many plant lineages possessed genetic flexibility that allowed them to quickly develop new survival strategies as conditions changed. Some species evolved the ability to switch between different metabolic pathways depending on water availability, essentially becoming metabolic shapeshifters that could thrive under a wide range of conditions. The most successful plant communities were those that developed mutualistic relationships with the expanding animal populations. Plants that could provide food, shelter, or other resources to animals often receive protection, seed dispersal services, or nutrient-rich waste products in return. These plant-animal partnerships became the foundation for increasingly complex ecosystem structures. Some of the most remarkable plant adaptations involved the development of chemical communication systems that allowed different plant species to coordinate their activities. Plants could warn their neighbors about herbivore attacks, share resources through underground root networks, and even coordinate their reproductive timing to maximize pollination success. The insect communities of this transitional period underwent their own remarkable transformations. The changing plant communities created new ecological niches that insects were quick to exploit. Some species developed highly specialized relationships with particular plant species, evolving intricate adaptations that allowed them to access resources that were unavailable to other insects. The diversity of insect life during this period was extraordinary, with new species appearing at rates that exceeded anything in the fossil record. The three-dimensional complexity that had characterized the flooded forests was being replaced by horizontal complexity as different plant communities created mosaic landscapes with distinct ecological zones. Flying insects proved particularly successful during this transition, as their mobility allowed them to exploit resources across multiple habitat types and respond quickly to changing environmental conditions. Some species developed migratory behaviors that allowed them to follow seasonal resource availability across vast distances, creating some of the first truly continental-scale animal movements. The predatory insects that had dominated the canopy layers of the aquatic forests adapted to the changing conditions by diversifying their hunting strategies. Some became ground-dwelling ambush predators, while others developed enhanced flight capabilities that allowed them to hunt over the expanding open landscapes. The most successful predatory insects were those that learned to exploit the abundant populations of herbivorous insects that were feeding on the rapidly expanding plant communities. The marine environments during this transitional period were experiencing their own significant changes. As the massive freshwater inputs from the continents began to decrease, ocean salinity levels started to return toward more normal ranges. This chemical shift had profound effects on marine ecosystems, favoring species that were adapted to higher salinity conditions, while creating challenges for those that had evolved during the period of massive freshwater dilution. The marine reptile communities that had flourished during the height of the aquatic age found themselves facing new competitive pressures as ocean chemistry changed. Some lineages proved adaptable enough to adjust to the new conditions, while others began a gradual decline that would eventually lead to their extinction. The most successful marine adaptations during this period were among species that had maintained some flexibility in their salinity tolerance. These creatures could move between different marine environments as conditions changed, exploiting resources in areas where less adaptable species were struggling to survive. The gradual return to more normal marine conditions also created opportunities for the evolution of new types of marine organisms. Species that had been unable to compete during the period of extreme freshwater influence began to diversify and expand, filling ecological niches that had been temporarily vacant. The atmospheric conditions during the transition period were creating unique opportunities for the development of new sensory capabilities among both terrestrial and marine organisms. The changing chemistry of the air and water created novel chemical gradients that some species learned to detect and interpret, giving them advantages in navigation, foraging, and predator avoidance. Some of the most remarkable sensory adaptations involved the detection of subtle changes in atmospheric pressure, humidity, and electromagnetic fields. Species that could sense approaching weather changes gained significant advantages in timing their activities and avoiding dangerous conditions. The electrical sensitivity that had evolved in some lineages during the storm-dominated aquatic period proved to be adaptable to the changing atmospheric conditions. Some species refined these abilities to detect the bioelectric fields of other organisms, while others learned to use electromagnetic navigation techniques that allowed them to maintain their orientation across vast landscapes. As the world continued its gradual emergence from the age of endless rains, the stage was being set for dramatic changes that would reshape the entire trajectory of life on Earth. The creatures that had learned to thrive in the transitional conditions between aquatic and terrestrial environments were developing capabilities that would soon allow them to dominate landscapes that were still taking shape. The small bipedal archosaurs that had survived and prospered during the aquatic age were now poised to inherit a world that was perfectly suited to their unique combination of adaptations. Their intelligence, social cooperation, metabolic efficiency, and behavioral flexibility had been honed during millions of years of life in challenging aquatic environments, and these same traits would prove to be exactly what was needed to succeed in the emerging terrestrial world. In the gradually clearing skies above the transforming landscapes, the future was beginning to take shape in ways that would have seemed impossible during the height of the endless rains. The lessons learned in the waterlogged world were about to be tested in entirely new environments, and the creatures that had mastered the art of adaptation were preparing to write the next chapter in the long story of life on Earth. The transition was far from complete, and many challenges lay ahead. But in the patient footsteps of small creatures crossing vast plains under skies that were slowly learning to clear, in the quiet conversations of social groups planning their next moves across unfamiliar territories, and in the steady rhythm of hearts that had learned to beat with the confidence of survivors, the seeds of future greatness were already germinating. The age of endless rains was drawing toward its close, but its legacy would endure in the bodies, minds, and spirits of the creatures that had been forged in its liquid embrace. They carried within them the memory of a time when water ruled the world, and that memory would guide them as they prepared to claim dominion over the dry lands that were slowly emerging from beneath the retreating floods. The retreat of the endless rains wasn't a sudden event, but a gradual unwinding that took place over hundreds of thousands of years. As the great volcanic systems that had sustained the deluge for so long began to exhale their final breaths, the atmospheric chemistry that had maintained the planet's aquatic state started to shift in ways that would fundamentally alter the trajectory of life itself. The first changes were almost imperceptible. noticed only by the most environmentally sensitive creatures that had learned to read the subtle signals of their world. Cloud formations that had persisted with clockwork regularity for millennia began to show small gaps, brief windows where actual sunlight could penetrate to the surface. These moments of illumination, lasting perhaps only minutes at first, were like glimpses of another world entirely. A world where light came directly from above rather than filtered through endless layers of water vapor. For plants that had evolved during the aquatic age, these brief exposures to direct sunlight were both revelation and challenge. Species that had adapted to the gentle, diffused light of the water-dominated world suddenly encountered the intense, focused energy of unfiltered solar radiation. Some withered under the assault, their delicate structures overwhelmed by the harsh brightness they had never experienced. Others discovered capabilities they didn't know they possessed, photosynthetic systems that could process direct sunlight with remarkable efficiency. The animals that had thrived in the perpetual twilight of the aquatic age faced their own adjustments to the changing light conditions. Eyes that had evolved to function in the murky, low-light environment of flooded forests suddenly had to cope with brilliant flashes of direct sunlight. Some species developed the ability to rapidly adjust their pupil size and light sensitivity, while others learned to seek shelter during the increasingly frequent periods of direct illumination. As the gaps in the cloud cover grew larger and more persistent, something extraordinary began to happen to the planet's weather patterns. The complex storm systems that had dominated the global climate for so long began to lose their coherence, fragmenting into smaller, more localized weather events. Instead of planetary-scale storm fronts that could persist for months, the atmosphere began to develop regional patterns that varied from place to place. This fragmentation of the global weather system created the first true climate zones that had existed in millions of years. Areas that had experienced identical conditions across vast distances now began to develop their own distinct characteristics. Some regions remained relatively moist, sustaining modified versions of the aquatic ecosystems that had dominated the world. Others began to experience extended dry periods that gradually extended into true drought conditions. The soil systems that had developed during the age of endless rains began to respond to these changing moisture patterns in ways that would reshape entire landscapes. In areas where the rains continued with some regularity, the incredibly rich organic soils that had accumulated over millions of years continued to support lush plant communities. But in regions where dry periods became more common, these same soils began to undergo chemical changes that would alter their structure and composition. The process was gradual but inexorable. Organic matter that had been preserved in waterlogged conditions began to decompose more rapidly when exposed to alternating wet and dry cycles. This decomposition released vast quantities of nutrients that had been locked away for eons, creating temporary surges of fertility that supported explosive plant growth. But it also began to change the physical structure of the soils, making them more susceptible to erosion and compaction. The early dinosauromorph lineages proved remarkably adept at exploiting these changing soil conditions. Their lightweight builds and efficient locomotion systems allowed them to traverse landscapes that were becoming increasingly unstable as soil structures changed. More importantly, their enhanced cognitive abilities enabled them to recognize and respond to the subtle environmental cues that indicated which areas were likely to remain stable and which might become treacherous. These intelligent creatures began to develop what could only be described as geological awareness, an understanding of landscape stability that went far beyond simple visual assessment. They could detect subtle changes in soil composition, recognize the warning signs of potential erosion or collapse, and identify areas where water tables were likely to remain stable even as surface conditions changed. This geological intelligence became a crucial survival tool as the landscape continued to transform. Areas that appeared stable on the surface might suddenly give way as underground water systems shifted or soil chemistry changed. Creatures that could anticipate these changes and avoid dangerous areas had enormous advantages over those that relied solely on immediate sensory input. The plant communities that emerged during this transitional period developed their own remarkable strategies for dealing with the changing environmental conditions. Some species evolved the ability to alter their root systems seasonally, developing shallow, extensive networks during wet periods and deep, concentrated systems during dry spells. Others developed specialized water storage organs that could sustain them through extended drought periods. The most successful plant adaptations involved the development of what botanists would later call phenotypic plasticity, the ability to dramatically alter their physical structure and physiological processes in response to environmental conditions. These plants could essentially transform themselves from aquatic to terrestrial forms as conditions required, maintaining their competitive edge across a wide range of environmental scenarios. Some plant communities began to develop cooperative networks that spanned entire watersheds. These botanical alliances involved species that could share resources through underground connections, coordinate their seasonal activities to maximize water retention, and even provide mutual protection against herbivores and environmental stresses. The most sophisticated of these networks could respond to environmental changes as unified systems, shifting their collective behavior to maintain ecosystem stability even as individual species faced challenging conditions. The herbivorous animals that had evolved during the aquatic age found themselves facing entirely new challenges as plant communities began to change. Species that had specialized in processing the soft, water-rich vegetation of the flooded forests suddenly encountered plants with tougher structures, different chemical compositions, and novel defensive strategies. Many herbivorous lineages underwent rapid evolutionary changes, developing more powerful digestive systems, stronger jaws, and new feeding behaviors. The most successful herbivorous adaptations involved the development of dietary flexibility. Animals that could process a wide variety of plant types, from soft aquatic vegetation to tough terrestrial foliage, maintained access to food resources even as plant communities shifted around them. Some species developed specialized gut bacteria that could break down cellulose and other tough plant compounds, while others evolved behavioral strategies that allowed them to select the most nutritious parts of plants while avoiding defensive chemicals. The carnivorous animals of this transitional period faced their own unique challenges and opportunities. The changing herbivore populations created fluctuating prey bases that required predators to be more adaptable in their hunting strategies. Some carnivorous lineages developed enhanced tracking abilities that allowed them to follow prey across increasingly diverse landscapes. Others evolved greater dietary flexibility, learning to exploit a wider range of prey species as traditional food sources became less predictable. The most successful predatory adaptations involved the development of cooperative hunting strategies. Groups of predators that could coordinate their activities, share information about prey movements, and execute complex hunting plans had significant advantages over solitary hunters in the changing landscape. These cooperative hunting groups often developed sophisticated communication systems and social hierarchies that maximized their effectiveness. The atmospheric chemistry during this transitional period was creating conditions that favored certain types of metabolic processes over others. The gradually decreasing humidity levels made it easier for air-breathing animals to regulate their internal temperature and moisture balance. Species that had struggled with the oppressive humidity of the aquatic age found themselves able to be more active for longer periods, as the air became drier and more conducive to efficient respiration. The changing atmospheric conditions also affected the way sounds traveled through the environment. The dense, humid air of the aquatic age had muffled and distorted acoustic signals, making long-distance communication difficult. As the air became drier and less dense, sound transmission improved dramatically, allowing animals to communicate across much greater distances than had been possible during the height of the endless rains. This improvement in acoustic communication had profound effects on social organization among many species. Groups that had been forced to remain in close proximity during the aquatic age could now coordinate their activities across much larger territories. Some species developed complex long-distance calling systems that allowed them to maintain social bonds and share information even when separated by many miles. The early dinosaur-morph lineages were among the first to fully exploit these improved acoustic communication possibilities. Their vocal apparatus, which had evolved during the aquatic age for close-range communication in dense vegetation, proved remarkably adaptable to long-distance signaling. Some groups developed elaborate vocal repertoires that could convey complex information about territory boundaries, resource locations, and social relationships across vast distances. The electromagnetic environment of the transitional period was also undergoing significant changes. The constant electrical activity that had characterized the storm-dominated aquatic age began to diminish as weather patterns became less violent and more localized. This reduction in atmospheric electrical activity created opportunities for animals with electromagnetic sensitivity to use these abilities in new ways. Some species began to use their electromagnetic senses for precision navigation, detecting subtle variations in the Earth's magnetic field that allowed them to maintain accurate directional orientation even across unfamiliar terrain. Others developed the ability to detect the electromagnetic signatures of underground water sources, giving them crucial advantages in finding reliable water supplies as surface water became less predictable. The most sophisticated electromagnetic adaptations involved the development of bioelectric communication systems. Some animals learned to generate and detect weak electrical fields that could carry information through conductive media like moist soil or shallow water. These bioelectric signals could travel much farther than chemical signals and were less affected by wind and weather conditions than acoustic communications. The marine environments during this period were experiencing their own dramatic transformations as the massive freshwater inputs from the continents began to stabilize at lower levels. Ocean salinity gradually increased toward more typical levels, creating conditions that favored different types of marine life than had thrived during the peak of the freshwater influx. The marine reptile communities that had evolved during the aquatic age faced significant challenges as ocean chemistry changed. Species that had become adapted to the brackish conditions created by massive freshwater inputs found themselves struggling in increasingly saline waters. Some lineages proved adaptable enough to adjust their physiology to the changing conditions, while others began a gradual decline that would eventually lead to their replacement by more salt-tolerant species. The changing marine conditions also created opportunities for the evolution of entirely new types of marine organisms. Species that had been unable to compete effectively during the period of extreme freshwater dilution began to diversify rapidly as more typical ocean conditions returned. These newly successful marine lineages often showed remarkable innovations in feeding strategies, locomotion, and reproduction that allowed them to exploit niches that had been temporarily vacant. The coastal environments, where freshwater systems met the changing oceans, became particularly dynamic during this transitional period. These boundary zones experienced constant fluctuations in salinity, temperature, and nutrient levels that created unique selective pressures. Species that could tolerate these rapidly changing conditions often found themselves in environments with reduced competition and abundant resources. Some of the most remarkable adaptations occurred among organisms that learned to actively exploit the environmental variability of these coastal transition zones. These species developed life cycles that were synchronized with the fluctuating conditions, timing their reproduction and growth phases to coincide with optimal environmental windows. The microbial communities that formed the foundation of all these changing ecosystems were themselves undergoing rapid evolution and reorganization. The shift from permanently waterlogged to seasonally variable moisture conditions created opportunities for entirely new types of microbial partnerships and metabolic pathways. Some microbial communities develop the ability to switch between different metabolic modes depending on moisture availability, essentially functioning as biological batteries that could store energy during favorable periods and release it during times of stress. These versatile microbial systems became crucial partners for larger organisms that were adapting to the increasingly variable environmental conditions. The most successful microbial adaptations involved the development of complex symbiotic relationships with plants and animals. These partnerships often involved multiple species of microorganisms working together to provide their hosts with enhanced abilities to process nutrients, resist diseases, or tolerate environmental stresses. The hosts, in turn, provided the microbial communities with stable habitats and reliable nutrient sources. As the transitional period continued, patterns began to emerge that suggested the world was moving toward a new type of environmental stability. Instead of the uniform aquatic conditions that had characterized the age of endless rains, the planet was developing a complex mosaic of different climate zones, each with its own distinct characteristics and biological communities. The creatures that were proving most successful in this emerging world were those that combined the adaptability they had learned during the aquatic age with new capabilities suited to the changing conditions. The early dinosauromorph lineages exemplified this combination of ancient wisdom and new innovation, using intelligence and cooperation strategies developed in the waterlogged world to exploit opportunities in the emerging terrestrial landscapes. These remarkable animals were beginning to show signs of capabilities that would eventually allow them to dominate entire ecosystems. Their problem-solving abilities were becoming more sophisticated, their social organizations more complex, their physical adaptations more refined with each passing generation. They were learning to think not just tactically about immediate survival needs, but strategically about long-term success in a world that was still defining itself. In the gradually stabilizing landscapes of this transformed world, where the memory of endless rains was slowly giving way to the promise of seasonal cycles and diverse habitats, these intelligent survivors were preparing to write the next chapter in Earth's long story. They carried within their genes and their behaviors the lessons learned during millions of years of aquatic existence. But they were also developing new capabilities that would serve them well in the terrestrial world that was slowly emerging from beneath the retreating waters. The age of endless rains was drawing to a close, but its influence would persist in ways both subtle and profound. The creatures that had been shaped by that aquatic crucible were about to inherit a world that was richer, more diverse, and more full of possibilities than anything that had existed before the first drops of that ancient deluge had begun to fall. In their footsteps, their calls echoing across landscapes still learning to be dry, lay the seeds of future dominion over a planet that was ready, at last, to support life forms that could dream beyond the boundaries of any single environment. The transformation was accelerating now, driven by forces that had been building for millions of years beneath the surface of the waterlogged world. Soon, very soon, the stage would be set for the emergence of creatures whose very footsteps would thunder across continents, whose shadows would darken skies, and whose legacy would endure long after the last memories of the endless rains had faded into the deep silence of geological time. As the last remnants of the endless rains finally began to fade into memory, something profound was stirring in the transformed landscapes of our planet. The world that emerged from those 2 million years of deluge was not simply a return to what had been before, but something entirely unprecedented in Earth's long history. It was as if the planet had used the endless waters as a vast laboratory, experimenting with new forms of life, new relationships between species, and new possibilities for what existence could become. The soils that had been enriched by millions of years of constant moisture and organic deposition were unlike anything that had ever existed. These weren't the thin, mineral-poor grounds of the pre-rain world, but deep, dark layers of fertility that could support plant communities of extraordinary abundance and diversity. Where water had once covered every surface, now vast prairies began to emerge, their grasses growing to heights that would dwarf modern grasslands, their root systems extending deep into the nutrient-rich earth. But these weren't simple grasslands. The plant communities that colonized the post-rain world carried with them the genetic memory of their aquatic origins, and many retained the ability to adapt rapidly to changing moisture conditions. Some grasses developed hollow stems that could store water during dry periods, while others evolved root systems that could tap into underground water reserves left behind by the retreating floods. The trees that began to populate these new landscapes were equally remarkable. Having evolved during the age of endless moisture, they possessed growth rates and structural capabilities that exceeded anything from the dry world that had come before. Some species could grow to full maturity in decades rather than centuries, their trunks expanding rapidly to take advantage of the rich soils and favorable growing conditions. The early dinosauromorph lineages found themselves inheriting a world that seemed almost designed for their unique combination of traits. The open landscapes that emerged as the waters receded provided perfect terrain for their efficient bipedal locomotion. The abundant plant life supported large populations of herbivorous prey species, while the complex topography created by the retreating waters offered numerous opportunities for territorial expansion and resource exploitation. These intelligent survivors began to demonstrate behaviors that went far beyond simple adaptation to new environments. They were actively shaping the landscapes they inhabited, creating trails that became permanent features of the terrain, establishing territorial markers that influenced the movement patterns of other species, and developing hunting strategies that modified the behavior of entire prey populations across vast regions. Some groups began to show what could only be described as agricultural instincts. They would systematically remove competing vegetation from areas where their preferred food plants were growing, effectively creating managed grazing areas that could support larger populations than would have been possible under natural conditions. These proto-agricultural activities weren't conscious in the way we might understand them, but they represented a level of environmental manipulation that had never been achieved by any previous animal species. The social structures that had evolved during the aquatic age became even more sophisticated as these creatures adapted to the new terrestrial environment. Groups that had learned to coordinate their activities across the three-dimensional complexity of flooded forests found that these same skills translated perfectly to managing territories that spanned hundreds of square miles of open landscape. Communication systems that had been developed for close-range interaction in dense vegetation evolved to function across the vast distances of the open plains. Some species developed long-distance calling systems that could coordinate the activities of group members separated by many miles, while others evolved visual signaling capabilities that use body postures and movements to convey complex information across open terrain. The most remarkable social development was the emergence of what researchers now recognize as cultural transmission on an unprecedented scale. Knowledge about seasonal patterns, resource locations, safe travel routes, and effective hunting strategies was being passed down through generations and shared between groups, creating bodies of collective wisdom that grew more sophisticated over time. Some lineages developed teaching behaviors that went beyond simple imitation learning. Adult animals would deliberately expose younger group members to challenging situations while providing guidance and protection, essentially creating educational experiences that accelerated the development of survival skills. These teaching systems allowed groups to adapt to new environments much more quickly than would have been possible through individual learning alone. The predatory strategies that evolved during this period were remarkable for their complexity and coordination. Groups of early dinosauromorphs learned to execute hunting plans that involved multiple phases, with different individuals taking on specialized roles that maximized the chances of success. Some would serve as scouts, identifying and tracking prey over long distances. Others would position themselves at strategic locations to cut off escape routes, while still others would execute the actual attack. These coordinated hunts required not just individual intelligence, but sophisticated communication and planning abilities. The animals involved had to understand not only their own role in the plan, but also how their actions would affect the behavior of their teammates and their prey. This level of strategic thinking represented a quantum leap in cognitive evolution that would have profound implications for the future development of intelligence on Earth. The metabolic innovations that had begun during the aquatic age continued to develop as the climate stabilized. The early dinosauromorph lineages were refining their ability to maintain consistent internal temperatures, developing more sophisticated cardiovascular systems, and improving their respiratory efficiency. These physiological advances allowed them to remain active across a much wider range of environmental conditions than any reptile had ever achieved. Some species began to show the first signs of what would eventually become true warm-blooded metabolism. They could maintain their activity levels during cool periods, remain alert during temperature fluctuations, and sustain high-energy behaviors for extended periods without the environmental warm-up periods that limited other reptiles. These metabolic advantages became particularly important as seasonal patterns began to establish themselves for the first time in millions of years. The ability to remain active during cooler seasons gave these creatures access to resources and opportunities that were unavailable to their cold-blooded competitors. They could hunt when other predators were sluggish, migrate during periods when other animals were inactive, and exploit seasonal resource pulses that required rapid response capabilities. The respiratory systems that had evolved for processing the oxygen-rich, humid air of the aquatic age proved remarkably adaptable to the changing atmospheric conditions. As humidity levels decreased and air density changed, these advanced breathing systems automatically adjusted their efficiency to maintain optimal oxygen delivery to active muscles and organs. Some lineages developed respiratory systems that were even more sophisticated than what would eventually evolve in birds and mammals. These creatures possessed air sac systems that allowed continuous airflow through their lungs, providing more efficient oxygen extraction than the bidirectional breathing systems of most vertebrates. This respiratory efficiency gave them enormous endurance advantages during long-distance travel and sustained physical activity. The sensory capabilities that had been honed during millions of years of navigating complex aquatic environments continued to evolve as the world became more terrestrial. Vision systems that had adapted to the murky, low-light conditions of flooded forests developed enhanced color perception and motion detection abilities that made them incredibly effective at spotting prey and predators across open landscapes. Hearing systems evolved to process the acoustic properties of the drier atmosphere, allowing for more precise localization of sounds and better discrimination between different types of acoustic signals. Some species developed the ability to detect infrasonic communications, low-frequency sounds that could travel for many miles across open terrain, enabling them to coordinate activities across vast territories. The electromagnetic sensitivities that had developed during the storm-dominated aquatic age found new applications in the more stable terrestrial environment. Some creatures learned to use these abilities for precise navigation, detecting subtle variations in the Earth's magnetic field that allowed them to maintain accurate orientation during long-distance migrations. Others developed the capability to sense underground water sources, giving them crucial advantages in finding reliable water supplies in the increasingly seasonal landscape. The chemical communication systems that had evolved for aquatic environments adapted to terrestrial conditions by becoming more sophisticated and longer-lasting. Scent marking became an important tool for territorial communication, with some species developing the ability to create complex chemical signatures that could convey detailed information about individual identity, reproductive status, and territorial boundaries. Some of the most advanced chemical communication systems involve the use of multiple compounds that could create layered messages. Different chemical components of a scent mark might degrade at different rates, allowing the message to change over time and provide information about how recently the mark had been made. This temporal dimension to chemical communication, added a new level of sophistication to territorial and social interactions. The reproductive strategies that had evolved during the aquatic age underwent significant modifications as environmental conditions became more predictable. The extended parental care systems that had developed in response to the challenging conditions of the waterlogged world continued to evolve, but now they incorporated new elements related to territorial establishment and resource management. Some species developed elaborate nest-building behaviors that involved not just creating protected spaces for eggs and young, but also modifying the local environment to create optimal conditions for offspring development. These modifications might include clearing vegetation to create open areas for temperature regulation, creating water retention systems to maintain local humidity, or establishing food caches to ensure reliable nutrition for growing young. The most sophisticated reproductive strategies involved multi-generational territory management, where family groups would maintain and improve territories over multiple breeding cycles. These long-term territorial investments allowed groups to create increasingly favorable conditions for raising offspring, leading to higher survival rates and more successful reproduction. The territorial behaviors themselves became incredibly complex, involving not just the defense of space, but the active management of resources within that space. Some groups developed what could only be described as landscape engineering capabilities, modifying drainage patterns to create optimal habitat conditions, managing vegetation to encourage the growth of preferred food species, and even influencing the behavior of prey species to make them more accessible. These landscape modifications weren't random or instinctive activities, but appeared to be based on sophisticated understanding of ecological relationships. The animals involved seemed to understand how changes in one part of their territory would affect conditions in other areas, and they could plan and execute modifications that would produce desired results over extended time periods. The tool use that had begun to emerge during the later stages of the aquatic age became more sophisticated and widespread as the terrestrial environment provided new opportunities and challenges. Some early dinosauromorph lineages learned to use rocks and sticks to extract food from crevices, create simple shelters, and modify their environment in ways that provided advantages over competitors. The most remarkable tool use behaviors involved the creation of composite tools, objects that were constructed from multiple materials to serve specific purposes. Some creatures learned to combine rocks with plant materials to create more effective digging implements, or to use different types of materials together to create more durable shelter structures. These tool use behaviors often involved forward planning and delayed gratification, with animals creating and maintaining tools in anticipation of future needs, rather than just responding to immediate challenges. This level of planning and preparation represented another significant advance in cognitive evolution that would prove crucial for future success. The landscape itself was continuing to evolve as the post-rain world established its new equilibrium. Rivers that had been massive torrents during the aquatic age settled into more manageable channels, creating systems of wetlands, floodplains, and seasonal water features that provided diverse habitat opportunities. These water features became focal points for biological diversity, supporting communities of plants and animals that maintained some of the aquatic adaptations developed during the age of endless rains. The soil systems that had developed during the long period of saturation began to mature and differentiate as drainage patterns established themselves and vegetation communities stabilized. Different soil types emerged in different areas, creating a mosaic of growing conditions that supported increasingly specialized plant communities. The atmospheric chemistry continued to evolve toward the conditions that would characterize the rest of the Mesozoic era. Oxygen levels remained high compared to modern standards, but were gradually decreasing from the extreme levels that had existed during the height of the aquatic age. Carbon dioxide levels were also stabilizing at concentrations that would support lush plant growth while allowing for more moderate global temperatures. These atmospheric changes created conditions that were ideal for the continued evolution and expansion of the early dinosaur-morph lineages. The high oxygen levels supported their advanced respiratory systems and active metabolisms, while the moderate carbon dioxide levels ensured abundant plant growth to support large herbivorous populations and the predators that fed on them. The seasonal patterns that were establishing themselves created new opportunities for species that could adapt their behavior to take advantage of predictable environmental cycles. Migration became possible for the first time in millions of years, as animals could move between different areas to exploit seasonal resource pulses or avoid unfavorable conditions. Some of the early dinosaur-morph lineages began to develop migratory behaviors that spanned entire continents. These migrations weren't just random movements in response to local conditions, but sophisticated journeys that involved navigation across vast distances, coordination between multiple groups, and precise timing to arrive at destinations when conditions were optimal. The navigational abilities required for these long-distance migrations were remarkable, involving the integration of multiple sensory inputs, including celestial navigation, magnetic field detection, landmark recognition, and possibly even infrasonic communication with distant groups. These navigational systems represented some of the most sophisticated biological information processing that had ever evolved. As the world continued to stabilize after the end of the endless rains, it became clear that the creatures that had survived and thrived during that extraordinary period had been fundamentally changed by their experience. They weren't just adapted to aquatic conditions that no longer existed, but had developed capabilities that made them uniquely suited to succeed in whatever environment the planet might offer. The early dinosaur-morph lineages were beginning to show signs of the characteristics that would eventually allow them to dominate terrestrial ecosystems for more than 160 million years. Their intelligence, social cooperation, metabolic efficiency, and adaptability were being refined and enhanced with each passing generation, creating the foundation for one of the most successful evolutionary radiations in Earth's history. In the emerging grasslands and forests of the post-rain world, where the sun shone directly through clear skies for the first time in millions of years, these remarkable creatures were taking their first steps toward a destiny that would reshape the entire planet. They moved with confidence across landscapes that were still learning to be dry, their calls echoing across vast distances, their eyes bright with an intelligence that had been forged in the crucible of endless change. The age of endless rains had ended, but its legacy lived on in the bodies, minds, and behaviors of the survivors who had endured its challenges and emerged stronger for the experience. The world they inherited was richer, more diverse, and more full of possibilities than anything that had existed before, and they were uniquely qualified to explore those possibilities to their fullest extent. In their measured footsteps across the newly stabilized Earth, in their coordinated movements across territories that spanned entire watersheds, and in their patient observations of a world still defining its new patterns, lay the seeds of dominion that would one day thunder across every continent, cast shadows across every landscape, and leave traces that would endure long after the stars themselves had changed their positions in the sky. The transformation was complete, but the story was just beginning. The endless rains had been the prologue to an even grander tale, one that would unfold over millions of years and reshape not just the land, but the very meaning of what it meant to be alive on planet Earth. The 2 million years of endless rain had left their mark not just on the landscapes and the creatures that inhabited them, but on the very fabric of time itself. As the final clouds began to disperse and the last of the great storms faded into memory, the world that emerged bore witness to one of the most extraordinary transformations in Earth's long history. This wasn't simply the end of unusual weather. It was the closing of one chapter in the planet's story and the opening of another that would echo through geological ages yet to come. The silence that followed the endless percussion of raindrops was profound in ways that transcended mere absence of sound. For creatures that had evolved amid the constant symphony of falling water, the quiet carried an almost mystical quality. Imagine ears that had never known stillness suddenly encountering the soft whisper of wind through dry grass, the distant call of a bird unmasked by the drumming of precipitation, the subtle rustle of leaves that were no longer perpetually heavy with moisture. This new acoustic landscape created opportunities for communication that had been impossible during the age of endless storms. Animals began to develop vocalizations that could carry across vast distances through the clear, dry air. Some early dinosaur-amorph lineages discovered that their calls could now travel for miles without being absorbed by the dense humidity that had once muffled every sound. They began to experiment with different frequencies, different rhythms, creating the first long-distance communication networks that spanned entire valleys and mountain ranges. The visual transformation was equally dramatic. Skies that had been grey and heavy for eons now revealed depths of blue that seemed infinite. The sun, that distant star that had been little more than a dim glow behind layers of clouds, suddenly blazed forth with an intensity that transformed everything it touched. Shadows, sharp and defined, appeared for the first time in the memory of any living creature, creating a new geometry of light and darkness that would fundamentally alter how animals navigated their world. Plants that had evolved in the perpetual twilight of the Rain Age suddenly found themselves basking in direct sunlight of unprecedented intensity. Some species, their photosynthetic systems overwhelmed by the sudden abundance of light energy, began to develop new strategies for managing this solar wealth. They evolved leaves with reflective surfaces that could regulate the amount of light they absorbed, or developed the ability to orient their foliage to track the sun's movement across the sky. The most remarkable botanical development was the emergence of what scientists now call solar tracking behaviors among certain plant species. These weren't simple tropisms, but sophisticated responses that involved the plant actively monitoring light conditions and adjusting its structure throughout the day to optimize photosynthetic efficiency. Some species developed the ability to fold their leaves during the hottest parts of the day to prevent damage, then unfurl them again when conditions became more favorable. The soil chemistry of the post-rain world was undergoing its own quiet revolution. The constant leaching that had characterized the age of endless water gradually ceased, allowing minerals and nutrients to accumulate in ways that created entirely new growing conditions. Soils that had been waterlogged for millions of years began to develop distinct layers and textures as drainage patterns established themselves and different types of organic matter began to accumulate. These maturing soil systems supported plant communities of unprecedented diversity and complexity. Where the Rain Age had favored generalist species that could tolerate constantly changing conditions, the stabilizing climate began to reward specialization. Plants evolved to exploit specific soil types, particular moisture regimes, and distinct seasonal patterns that were becoming established for the first time in geological ages. The early dinosaur-amorph lineages found themselves inheriting a world that seemed almost tailored to their unique combination of adaptations. Their bipedal locomotion, which had originally evolved for navigating through shallow water and dense vegetation, proved perfectly suited for covering the vast distances of the emerging open landscapes. Their enhanced cardiovascular and respiratory systems allowed them to maintain high activity levels during long-distance travel, while their sophisticated sensory capabilities enabled them to navigate confidently across unfamiliar terrain. These creatures began to demonstrate behavioral innovations that went far beyond simple adaptation to new environmental conditions. They were developing what could only be described as landscape awareness, an understanding of how different parts of their territory were connected by water flow, seasonal patterns, and resource availability. This geographical intelligence allowed them to make strategic decisions about where to establish territories, when to migrate between different areas, and how to exploit seasonal resource pulses most effectively. Some groups began to show signs of what researchers now recognize as proto-cartographic abilities. They could maintain accurate mental maps of vast territories, remember the locations of seasonal resources that might only be available for brief periods, and plan complex journeys that took advantage of favorable conditions across multiple habitat types. These navigational capabilities were supported by increasingly sophisticated memory systems that could store and retrieve complex spatial and temporal information. The social structures that had evolved during the aquatic age continued to develop in response to the new terrestrial environment. Groups that had learned to cooperate in the challenging conditions of the waterlogged world found that these same cooperative abilities gave them enormous advantages in exploiting the resources of the post-rain landscape. They could coordinate hunting activities across vast territories, share information about distant resource locations, and provide mutual protection during long-distance migrations. The communication systems that supported these social structures became increasingly sophisticated as the acoustic properties of the environment improved. Some species developed elaborate vocal repertoires that could convey complex information about individual identity, emotional states, territorial boundaries, and resource availability. These vocalizations weren't just simple calls, but structured communications that showed evidence of grammatical organization and semantic complexity. The most remarkable social development was the emergence of what can only be described as cultural institutions among certain dinosauromorph lineages. Knowledge about successful hunting strategies, effective territorial management techniques, and seasonal behavior patterns was being preserved and transmitted across generations through sophisticated teaching and learning systems. These cultural traditions allowed groups to accumulate wisdom over time, creating bodies of collective knowledge that gave them significant advantages over competitors who relied solely on individual learning. Some lineages began to develop what could be called technological traditions, standardized techniques for manipulating their environment that were passed down through generations and gradually refined over time. These might include specific methods for creating shelters, techniques for processing food, or strategies for modifying local habitat conditions to make them more favorable for the group. The metabolic innovations that had begun during the aquatic age reached new levels of sophistication as the climate stabilized. The early dinosauromorph lineages were developing increasingly efficient systems for regulating their internal temperature, managing their energy expenditure, and maintaining consistent activity levels across a wide range of environmental conditions. These physiological advances were crucial for success in the post-rain world, where seasonal variations in temperature and resource availability required greater metabolic flexibility than had been necessary during the more stable conditions of the aquatic age. Some species began to show the first clear signs of what would eventually become true endothermic metabolism. They could maintain their body temperature within narrow ranges, regardless of environmental conditions, remain active during cool periods that rendered other reptiles sluggish, and sustain high-energy behaviors for extended periods without requiring external heat sources for warm-up. These metabolic capabilities were particularly important for species that were beginning to exploit the seasonal patterns that were establishing themselves across the post-rain world. The ability to remain active during cooler seasons allowed them to take advantage of resource opportunities that were unavailable to cold-blooded competitors, while their enhanced endurance enabled them to undertake long-distance migrations that opened up entirely new territories for colonization. As we drift toward the end of this ancient journey together, I want you to imagine one final scene. Picture those small bipedal creatures standing on a hilltop as the last clouds finally part, revealing a world transformed beyond recognition. The endless percussion of rain has given way to profound silence, broken only by the whisper of wind through grass that had never known drought. In that moment of stillness, as sunlight touches the earth directly for the first time in 2 million years, the future of our planet was quietly taking shape. The Carnian pluvial event wasn't just a period of unusual weather. It was evolution's greatest experiment, a planetary reset that cleared the stage for life to explore possibilities that had never existed before. From the chaos of endless storms emerged creatures with capabilities that would one day shake continents, cast shadows across entire ecosystems, and leave footprints in stone that we can still trace today. The dinosaurs didn't inherit the Earth through conquest or dominance. They inherited it through adaptation, intelligence, and the quiet persistence of survivors who had learned to thrive when the very rules of existence were being rewritten. In their patient footsteps across landscapes still learning to be dry, we can trace the beginnings of one of the most successful evolutionary stories our planet has ever known. The endless rains had ended, but their legacy lives on in every breath we take, every step we make across this transformed world. Because sometimes, the greatest changes come not with thunder, but with the gentle persistence of water reshaping stone, one drop at a time. Thank you for joining me in this quiet corner of deep time. If this journey stirred something in you, I'd love to hear where you're listening from tonight. Until our paths cross again in another ancient story, sleep well and dream of the endless possibilities that rain can bring.